Yeah, hi, good evening, everyone. So, welcome to the week 2 solving session. So, we will discuss some problems like as the previous. So, let me. So, I hope you all have this Replit team access.
Yes, sir.
Okay. If anyone have if anyone don't have, then you can see the invite link on the calendar event. We have already saved that invite link on the calendar event, and you can join the team. Otherwise, we have also released these problems on the portal. Okay, so you can also solve these problems on the portal after this session. So let me share my screen and let me release the problem. So we have total 4 problems today based on the week 2. Uh, I'm releasing all 4 problems. Okay, so now you can refresh your screen and you can see the problems. Okay, on the Replit team. If anyone have not joined this team, I'm sharing the links in the chat. Okay, so I've sent the link in the chat. If anyone have not joined yet, you can join. Okay.
Sir, could you also please explain bubble sort?
Okay, bubble sort. But bubble sort is not part of the course. Still, you want to know?
Yes, sir, I wanted to know. It's one of the three I'd learned. I've heard about it. Bubble sort.
Okay. Okay, so sure that we will explain that. So okay, so meanwhile, others can start the problem number 1. Okay, so just read the problem statement, figure out the logic, and if you figure out the logic, then you can start the coding also. And after that, we will discuss. Okay, after 5 or 10 minutes, we will discuss the logic first, and then we will discuss the solution. Okay,
Sir, for which week we are going to do?
week 2.
Okay.
Uh, you have to open the Replit team.
Yeah. Okay.
Okay,
Thank you.
so and refresh the Replit team, and then you can see the new problems in week 2. Okay, so yeah, regarding the bubble sort, let me share my notepad. Okay, so regarding the bubble sort, suppose we have one input list, and input list we have any random element like this 3, 5, 1, 4, 2, 8, 6. Okay, so how the bubble sort actually works? Okay, so suppose this is a list, and where we have this index 0, 1, 2, 3, 4, 5, 6. Okay, total we have 7 element in this list. And what we will do, we will run some pass. Okay, pass means iteration we will run, and in every iteration we will compare the element with the neighbor elements. Okay, and we can start this comparison from the start also, or we can start this comparison from previous also. So what we can do, suppose if we are in the first iteration. Okay, so first iteration, what we are doing, we are running from the previous elements, and this previous elements, and we will compare this previous element with their next second last element. Okay, so this 8 and 6 we will compare, or we can start the same things from this side. Okay, from left side. Suppose we are starting from this side. Okay, so what we will do, we will compare these two elements. If these two elements are in the correct order, okay, correct order means what is our required goal is, so we want to sort this list in the increasing order. Okay, so that means all elements should come, so every element should be greater than to the previous elements. So this should be the order. So here we can see that this 3 and 5 are the correct required order. Okay, so 3 and 5 are the sorted order. So we will move to the next pair. So like this 5 and 1. Okay, so 5 and 1, you can see this pair is not in the correct required order. So what we will do, we will just swap the elements, and the previous element will remain same, and this will become 1 and 5. Okay, in this. Now we will check this 5 and 4. Okay, so this 5 and 4, is this in the correct order?
No.
No. So we will swap this. Okay, so we will perform the swap between this. So now our list will update like this. So 3, 1, 4, and 5, 2, 8, 6. Okay. Now next things we will update. We will check this next pair. Okay, 5 and 2. Still, this is also not in the correct order. So we will update our list. So 1, 4, 2, 5, and 8, 6. Now we will compare this pair. Okay, so 5 and 8. So here this is in the correct order. So no change. Then again in the next iteration, we will check this 8 and 6. So here we will again swap the elements. So 3, 1, 4, 2, 5, 6, 8. Okay. So this is one pass. This is the first iteration. In this pass, we are comparing each pair elements from the first, and after completion of this iteration, complete iteration, what we can see, the maximum element is coming at the correct position. Okay, so this maximum element is now coming at the correct position.
Yes, sir.
Now we will repeat the same process again. Okay, and second iteration, and we will start the same process. Okay, now 3 and 1. So now you can see 1, 3, then 4, 2, 5, 6, 8, then 3 and 4. Okay, it is already in sorted order. Now 4 and 2. So now it will become 1, 3, 2, 4, 5, 6, 8. Okay. Now 4 and 5 is in the correct order. 5, 6 is already correct in the correct order, and 6 and 8. Okay. So in the second iteration, now 6 is also, we can see that this is in the correct place. So in this way, in the every pass, okay, in the every pass, one element will come at the correct place. One maximum element will come at the correct place. So in this way, our element will be sorted from the previous one by one. So all elements will shifted into the correct place, and all elements will be sorted in this process. So this is called as a bubble sort process. So bubble is this name is also given in the conceptual way. So what we are doing, we are just comparing the element like this. Okay. So in the pair wise. So if we just like draw this, so this is look like bubble things. Because of that, some name convention is there.
So
Okay.
how do we decide how many iterations and when to stop?
No, so you have to complete the process. You cannot stop the process in between. You have to complete the process. So that means how many elements we have? We have 7 elements. You have to run this loop 7 times.
Okay.
We have to run 2 loops basically. First is the outer loop, so that will decide this outer iteration, and second loop for this process comparison.
So
Nested loop.
this will be like n into n, right?
Yeah, n into n. So n square is the complex.
So could you provide the code, just the for loop?
So for loop we can run. So let me open the replit.
Yes, sir.
Okay, so
So then it is not a very efficient sort, right?
no, this is not efficient. This is a very costly, actually, similar to your selection sort.
Okay.
Who said that this is the efficient approach?
No. I mean, I'm just when it is n square, basically.
Yeah, this is because of that. Professor has not discussed this bubble sort because this is not good efficient approach.
Okay.
Okay, so let me create one. This is the home. Okay. Python PDSC. Okay, so what we can do, we can write like a function. So def and bu bubble. Okay, and we are taking one list in the input, and inside this list, what we can do, we can run a loop. So for I in range and the len of L. Okay, len of L, and inside this another loop for j in range Same thing, we can run len of okay, so len of L we can run. Okay, and here we can check like if so we are running this loop. Okay, so we can run this loop one less than, because okay, so to compare the elements. And what we will do in the every process, so we will check if that L, okay, so L of I, sorry, L of J uh, is uh, greater than, okay, is greater than of
Sir,
L of J plus 1.
sir, the inner loops can start from 1, right? 1
Uh,
to len of L minus 1.
no, actually we are, what we are doing, we are comparing the first element. So if zero index element with the first index element.
Okay, you are taking inside J plus 1. Okay.
Yes, okay. Yeah, so this is the comparison. If the previous element is greater than to the next element, so we will perform the swap. So here we will perform the swap. So Lj comma Lj plus 1, and here is Lj plus 1, and that comma Lj. Okay.
So equal to.
Okay, equal is missed. Okay, so this is the swapping, and this is the only loop we need. So for I in divide, this is I is not used. Okay, no problem. And after that, we will return. So, L. Okay, so this is in place sorting. Basically, we are sorting the elements in the same place. And what we can do, we can take one list. So like L equal to 3 1 random element. So if we pass this, print
Sir, is it stable, sir, or unstable?
bubble sort. Okay, so bubble sort basically, yeah, it is depends on the implementation. Sort I think is not stable. Okay, so let me just first run this and we'll discuss things. So bubble and that L. Okay, yeah, now we are getting the correct sorted output. So this is the very easy way to implement this bubble sort.
Yes.
And regarding this, yeah, you can now think about this. Is there any counter example you have where this bubble sort will return the unstable output? So what's the process actually we are doing? We are just arranging the elements. So we are
If
comparing
we
the.
have multiple similar values, right? Then it's unstable, correct?
So stable is actually we check when we have the similar value in the list.
Yeah.
That is actually the property of stable things. We need stable element. We need similar elements with the same value. If that values elements are actually coming in the same order as input, that we can say that our algorithm is a stable algorithm. Otherwise, not stable. So here, is there any way? So our order of similar elements is changing. Like if you're taking 1, 2 is here, and another 2 is here.
No, sir.
So what we are doing? We are just comparing the element. Okay,
I
so
guess it's a stable sort because we are not
yeah,
switching it. It's not equal to, it's only greater than.
did that. So actually, we are comparing only the neighbor element every time, and so that means this first two element will never become after this. So we are not performing swapping between the two far positions like the selection sort. In selection sort, what happen actually? We find out the min element position and then we swap with the first position element or second position element like this. So in that case, actually, there is a chance our similar value element may be shifted, our order may be changed. But here, actually, it is not looking like this. So the similar value element cannot, this position cannot be changed. Okay, so in any way. So this bubble sort is actually stable sort algorithm.
Sir, I've also heard about radix sort. Is that important or it's fine?
Mm, you can just explore this, but that is not too much important. Regarding this uh, current this PDSA course, it is not in the syllabus, but still you can explore what is the concept of the radix.
So is
Okay,
that
so radix basically we
square?
used when we used to sort the element where we have that large number, actually large number of elements. So where it number contains many digits, like, so we can sort the numbers digit wise. First we sort the elements by the first digit, then second digit, like this. So we apply this logic in the radix sort.
So is that also n square?
No, that is not n square. That is actually linear actually.
So okay, it's a better sort.
Yeah, that is based on the that how many digits are there actually in the numbers.
Okay, sir.
The complexity depends on the number of digits.
Okay, sir.
Okay. Yeah. So this is bubble sort. Okay. Let's move to the problems. Okay. So this is it. Okay. So in week 2 now, this sorting algorithm you have already see, and also binary search you have already seen. Okay, so regarding the binary search algorithm, there is one important things, because if you are using any data structure, okay, from the here we are using Python. Okay, so if you are using Python, and Python provides many built-in function on the data structures. So before using this built-in function and any shortcut things which is already provided by the data structure, so you should also know that how much time actually that operations are taking. Okay, so that's are also required, because if you are writing any solution, and maybe sometimes you will not get a efficient solution, because your built-in operation may be taking more time. So one implementation I have mentioned in the notes, which professor have also discussed during the lecture, this binary search implementation. So if you know this binary search, open. So you know the binary concept. In binary search concept, if we have any sorted sequence, okay, and then we can search the element by the help of dividing and conquer rule, and we can just check the middle element, and we can decide which part we can remove for the next search, and which part we will search in the next iteration. And in that way, every time we will remove the half of the space for searching. So in this way, our time will reduce to the log n. Okay, but suppose what happened here, one implementation is discussed using the slicing. This one. Okay, so professor have also discussed this in the code. So here, if you are using this slicing operation on the list, so what happening actually internally? You know this slicing operation. What is the purpose of this slicing? If we are here, we are using recursive function. Okay, so this is a recursive function, and every time we are when we are passing this slicing list, so what happening? Are the so the same list is passing, or new list is actually passed?
New list.
Same list.
So you are saying that same object is passing.
It's a new
New
getting
list.
No.
called
List
by
to
reference.
Okay.
A copy is made of it.
So I have written this function here, and this L, this is way the condition are this. Okay, and I'm calling this. What is returning? Is returning true and false. It is returning true anywhere. Okay, return mid. Okay, index it is. Bit, no, it is returning index. Okay, so let me check. Yeah, fourth index. Okay, so let me check the ID of the list. Okay, which is creating inside. Okay. So what we can do, we can write the print operation, print that id of L. Okay, so now let's see, yeah, is this okay, so we are printing directly. Okay, what's hmm. So here you can see, in the first actually previous example, when I call this with L5, so what happened actually, the we have checked the middle element and we found the element in the first tracer, first in the first recursive call. So because of that, we find only the one ID. But this time actually I'm calling the searching element K. Okay, so this we are searching 2 in the list. So here actually there are 3 recursive call happens, and every time you can see the ID of the list which we are printing for L, this is different. Okay, so here 2 4, here 3 2, you can see the ID is different. So we can see that this list is actually are not the same for the every call. This list is not same. When you are using this list slicing operation, what happens, actually new list is created. That new list is created, and half of the elements which you are what range actually you are using with the help of slicing, that number of elements actually copying to the new list, and that list actually passed. Okay, so this operation actually internally takes order of n time. So suppose if you have n elements, and here you are calling this recursive function with n by 2. So n by 2 is also called as the order of n operation. So that copy operation which is happening inside this list slicing operation, all elements, half of the elements are actually copying into the new list. So that operation is actually taking order of n time, and your goal is of this binary search is log n. Okay, so if any of the one operation is taking order of n time, then overall complexity will become order of n for this function. Okay, so sometimes what happen, if you are writing this implementation for any problem where the log n complexity is required, so this code maybe will not pass the test case. Okay, you will not get the log n time complexity with this code. Okay, because of this slicing operation. So you can write the same implementation, same concept with the help of another approach. You can use the iterative method, or you can use the same binary search recursive approach, but you can pass the same list without using the slicing. So you can see here, this is also a recursive approach, but here we are passing the same list L. Okay, we are not using slicing here. And what part actually we need to search in the next call, that we are deciding with this index, actually what is the low index and what is the high index will be the in the next call. So we are passing this low index and high index every time, and based on that we are searching the area. So if I call this okay, so initially we will pass like this, so v and 0, and what is our last index. So 0 1 2 0 1 2 3 4 5 6 7 7. Okay, so this is the initial binary search, the function name is same. Okay, everything is okay. So now this is 1, yeah, 1 index it is returning. Okay, and let check this index, that id of L. So print at id of L. So you can see we are getting the same id 64 64. Okay, so here this means we are passing just a name of the object, and inside every recursive call we are accessing the same list. We are not creating any new list in the recursive call, and with the help of this index value, low value, and what we are passing at the high value, based on that we will decide in the next iteration that which part we will check for the next iteration. Okay, so here this code is actually will provide the log n complexity. Okay, and Another way, you can also use the iterative method. So that is also one way without recursive method. So that is this one. Okay, here you are using while loop, and you can decide, you can calculate the mid element every time, and after that just check. So this while this inside this iteration we will decide the part. Okay. So this is also a log n code. Yeah. Okay, so this is the one important thing. So same things, if you are performing some list like pop operation, that insert operation, or append operation, so you should know how much time that actually these operations are taking. So if you are using append operation at the end position, okay, in the list, so that actually that operation will take order of one time, constant time, okay, because you are adding the element at the last, so there is no operation are performing with the other elements. But suppose if you are inserting any element at the first position, so suppose if you are using any insert method and you are adding one new element at the first index, okay, so what will happen actually, all elements remaining n elements will shift to the one position to the right. So all index will be updated actually. Okay, so if you are adding new element at zero index, so previous zero index element will be shifted to the first index, then first index element will be shifted to the second index. So that operation will be happen with the each element. Okay, so that operation will become order of n element. Okay, similar for the pop. So if you are using pop operation from the end, so all that will take all constant time. But if you are using pop operation with in between or from the first index, so that will take order of n time. So just also focus on this. What type, if you are using any operation with the data structure, so what is the possible complexity for that? Okay, so first problem today we have this. Let me open the another scenario. This one.
Sir, could you share this link?
Which link?
The Replit link.
What happened? This is working fine. Oh, what is this? Problem. Yeah, it is working fine. What issue you are facing with the Replit link?
No, sir, I got it. I just wanted the Replit link. Someone sent it in the chat.
Okay, fine. Otherwise, the Replit invite link is already available in the calendar event. Yes. Okay.
Okay, sir.
Okay, so the first problem is basically uh, can anyone tell me what concept you can use for the first problem? First thing, just read the problem statement carefully and understand that what type of input is you have.
So I think we can use binary search.
Okay, you can use binary search. Okay. How you decided this?
Like we have to find the largest element, which means
Okay.
the array is almost sorted. So I thought if we set some constraints, we can find through binary search. We just want to modify binary search algorithm, I guess.
Yeah, you are saying correct. So here, but according to the binary search, all elements are sorted into the increasing order. So we cannot use as it is that binary search. We have to decide that how we can use the similar concept of the binary search here. Okay, so what type of order we have here? So you can just read the problem statement, write a function find peak.
Sir,
Yes.
sorry to interrupt you, but which problem you are solving?
Problem one, week to live coding problem one.
Okay, sir.
Okay. So we are discussing only live coding problems in this session. So that we have just released on the Replit, and that same problems are also released on the portal. Okay, how many of you know that we have released new UI of the portal today? Any of you have tried?
Yes, sir. That was so good, sir.
Okay, okay, yeah. So just give the feedback if you are facing difficulty. Okay, so just give the feedback for that also. Okay, so that is actually released in the beta testing purpose. So if any problem is there, then that it will be resolved.
Where can we see
So
that,
which
sir?
for which section, sir?
That if you see the course page, okay, so this is the course page. Suppose if you are opening any programming assignments, any programming problem like this PA1, okay. Now
That
this
is
type,
similar to the lead code platform. Okay.
no, sorry, what you're saying? Can you repeat?
I mean, that is similar to the lead code
Yes, yes, yes.
interface.
Yeah, correct, correct. So here you can see this was the previous UI. Okay, so you can use this also right now, and there is one tab. It is given on the right top. Try new UI. Okay, for the programming problem. Now you can see this new interface. So here you have the problem statement on the left. Some tabs are there internally. So question, test cases, solution. So the solution will be visible after the deadline. So you can just, and here on the right side you can write the code. So some features are still not open. Okay, so like this debug on the side, this is actually still under developing phase. Okay, so team are working on this. The remaining things are you can just explore. Okay, so test run button is there, submit button is there. Just try to use it.
So this is far more better than the previous ones, sir.
Yeah. So
Jobs. It's very
so we are just trying to improve also. So maybe some problem you will face during the testing. So just report it. Okay. Yeah. So okay. So repeat the problem. Yeah. This find we second problem. Write a function find peak L that accept a list L of n distinct elements. Okay. So first thing, our elements are distinct. Okay. And returns the peak element of the list. A list element is a peak if it is greater than its neighbor. For corner elements, we need to consider only one neighbors. Write a solution of log n. Okay, so here log this it is mentioned in the problem statement. Write a solution of log n complexity. Consider that there is only one peak is in the list. Okay, so all elements are distinct. This is the first constraint it is given, and only one maximum elements are possible in this case. So this here last condition is also given. So that means there is only one peak possible in this. So what type of order is possible for the input? Okay, so input order is possible like this. So suppose if you have a list, so this is list. If I draw the order, okay, so there is a chance the elements are increasing in this way. Okay, so this is the smallest and this is the maximum. This is the first element. Okay, so this is the first element, this is the last element, and all elements are increasing in this way. Another, what are the possible order is decreasing order. Okay, so this is the maximum element, this is the smallest element. Okay, so this is the first element, this is the last element. So all elements are in decreasing order. So here this is the peak, and here this is the peak. And another possibility is here the first element, and it is elements are increasing till some point. After that, it is all elements are decreasing. Okay, so this is the peak element in this case. So these are the three possibility of the input we have for this problem.
Sir, can you say the
Isn't
first two
it
possibilities again?
Sorry,
Sir, can you say the first two possibilities again?
this first condition.
Yeah.
Okay, so yeah, what happened actually? Suppose if your list is like this type 1, 2, 3, 4, 5, 6, 7, all elements are distinct here, and here this is the peak element. Okay, so we can say that elements are increasing in this order. Another possibility is if our elements are in decreasing order, like 7, 6, 5, 4, 3, 2, 1. Okay, So then this is the condition like this. Okay, so here peak element is coming at the first position. And another possibility is we have like this. So 1, 3, 6, 8, 10, and then 9, 7, 5, 4, 2, like this. Okay. So here elements, first elements are increasing and then decreasing. So there is one peak is possible. Okay. So this is mentioned in the problem statements. Only one peak is possible. So in this case, if we follow this condition, so only these three types of possibilities are there for the input. Now you have these three possibility, and here some order is there. Okay, so either you have this increasing order or maybe a decreasing order and this type of order, increasing and then decreasing. Now you can decide the approach how you can solve this in the log n time.
So log n, basically that means we have to do divide by 2 approach.
Yes,
So take the
yes,
midpoint
correct.
value.
Hmm.
Because otherwise it's, if you do the simple linear search, it will become n.
Order of n, yeah, correct. So what
So
happened actually, you can try in the Python, you can simply try that, like what is the max of L, return max of L. Okay, so here maybe there is a chance, so not chance actually, in Replit actually you can pass the test case with the help of this max L. But
correct.
on portal actually some large test case are configured. So let me open the same problems on the portal. Actually you can see the all test case on the Replit. Because of that we not configured the last test case on the Replit, but portal we have configured. So yeah, first problem. Okay, so this is the peak. Okay, so let's
So how much time does max take?
so that
So
actually takes the order of n. That takes the order of n.
okay, sir.
Okay, so let's return max of L. Okay, so this is the possible solution for this. And if you run this, let's see how many test cases are passed on the new UI. Okay, so you can see some test cases are passed. Case 1 is passed. Okay, case 2 is passed in the public test case. Case 3 and case 4 is not passed. Okay, we have also configured in this way, so you can also see the that machine time. What is the your code execution time and what is the expected time? Okay, so you can just take get some idea why your code is not passing the test case. Okay, so here your execution time is actually higher if you are using this max L. Okay, if you run the submit that private test case, so you can see 0 out of 3 private test case passed, because all the private test case are large in the size. So if this test case are small actually, so here you can see we have only 4 elements in the input. So in that case, that cannot be validate actually, because the time is very less in the both case, either in order of n or log n. Okay, so that cannot be validated. But
We
for
are
the
less
large
than
test
the
case,
expected time.
yeah, expected time. No,
We are
you
less
are
than,
not. No, you are not less than. Sorry, here
it
it is
showed 3
given e.
seconds.
No, you missed this. E to the power -5 is also mentioned.
Okay. Okay, sir.
Okay, this is not less. Okay, so just use the correct approach. Here, same things. If you use the slicing, still that will not pass the test case. That code will not pass test case. So just try to implement with the help of any such tree concept. Also, don't use the slicing.
Sir, I have a doubt. This time, is it based on the return or the whole program we write?
No, whole program.
Whole program. Okay.
Sir,
Yes.
is there any proper structure of the input list? I mean, is it a random or like there will be peak in the middle or at the left side or right side?
No,
Is
what
there any random
I'm
division?
not getting what you are saying. Some voice problem is there. So what you are saying?
Sir, actually, I'm saying, sir, is there any proper structure of this list, input list here?
No, as I mentioned, according to the problem statement, if you read the problem statement, so what is given that the elements are distinct. Okay, elements are not repeating, and after that there is only one peak is possible in the list. So if you fulfill this criteria, so you will only get this three type of situation in the list. Otherwise, if you take any random list like 1, 2, 3, and then suppose like this is 4, then 3, then 6, then 5, like this. So in this case, or this peak definition is also defined. So like what is the peak definition? Okay, so a list element is a peak if it is greater than its neighbor. Okay, and in the corner case, if it is greater than the only one neighbors, if maximum is exists on the corner side. So here you can see this 4 is also can be considered as a peak because this 4 is greater than 2 and 3. Same way, same things we can also say with 6. 6 is also maybe peak because this is greater than 3 and 5. So this is not the possible input for this case because it is mentioned that in the question statement only one peak is there. So if we fulfill this condition, so only this third this image, this is the third case, this first case, and the second case. These are the only possible case of the input. Okay, here only one peak is there. This also one peak is there, and this is another peak is possibility. So how you can identify this and how you can use the binary search concept here?
Sir, I think only for the middle, when the peak is at the middle, then only we have to use binary. Otherwise, we can just return L of 0 or L minus 1 by comparing it to the neighbor.
Yeah. So, okay, that is fine. So first condition you are saying then, if we check that if L of 0 is greater than L of 1, okay, then we can directly return the answer.
Yeah,
L of
similarly
0.
for the ascending
Okay.
order.
Yeah, this is for the first condition you can directly use. Second condition you can use if L of minus 1 is greater than L of minus 2. Okay, then you can directly return this L of minus 1. Okay, so these two conditions you can directly use for the corner case. Correct. Okay, so yeah, these two corner cases are covered in this constant time operation. Third case, how you can decide?
When the mid is larger than the neighbors.
Yes. So the condition for the identification of the peak element is actually if L of m is greater than L of m minus 1, okay, and greater than of L of m plus 1. If this condition is satisfied, you can directly return this answer, L of m. Correct? So this is for the identification of the peak element. If this condition is satisfied for middle element, you can return the answer. But there is a chance you will get this type of situation. Okay, so here L of m is greater than, so there is a two possibility of the condition. So L of m minus 1 and like this, L of m minus 1, m plus 1. If you are getting this situation, what you will do?
Take the like m plus 1 element.
So what you can decide, you can check this condition. If this condition is true, then you can return the answer. Otherwise, you can check this condition. Okay. So what happening if this condition is true? So that means elements are in increasing order. Okay, so that means this lm minus 1 is, suppose this one is there, m is like this, and this m plus 1 is this. So elements are in increasing in this order. So that means peak element will come on the right side, on the right side. So that means you can skip the elements which are coming before this lm completely. Okay, so if this condition is true, you can directly read, that means what is the case actually. So that means your middle is coming on this side, this increasing this side. Okay, and at this time of, suppose if this you are getting this mid, okay, and m plus 1 is like this, m plus 1, m minus 1 is this, m minus 1. Okay, and suppose you got this middle element like this point. So that means elements are in increasing order. So that means m minus 1 is smaller than m, then m is smaller than m plus 1. So elements increasing direction is going to the right side. So what you can do in the next process, you can completely remove this part for the search and just move to the check for the right part. So just remove the half part and just check for the right part. And in some position, suppose if you are getting the reverse condition, so same things, L of m is like smaller, sorry, greater. Yeah, m, L of m minus 1, and this is greater of L of m plus 1. Suppose if you are getting this type of situation, so that means you are lying in this, okay, where the elements are decreasing. Okay, so in this case, you have to check this side, left side, and you can directly skip the right side. Right half you can ignore. So based on these three conditions, you can decide where you need to search next and which part you can ignore.
Sir, if this happens, so directly we can see if it's in the left side, L of 0 is the highest one, right? Because it's in sorted order.
No. Yeah, no. So this is not the always case. What you are saying? Can you repeat?
Now, if the L of m is less than L of m plus 1 and it's less than the L minus 1, so this means that it's in the left part. So it will be the first element, right? Because it's
No,
in
not
sorted
first
order.
element. Not first element. We cannot say that that element will come at the first element. So what happens? Suppose this is a case for the input 1, 10, and then a 9, 8, 7, 6, 5, 4, 3, 2, 1. Sorry, not 1. Okay, all elements are distinct. Okay, so this is the case. Here, peak is coming at this point. Okay, suppose if you are checking directly middle element. So suppose if you are getting this middle element is 6. Okay, so this is m. Here this is m plus 1 and this is m minus 1. Okay, index. And what condition you are getting? 7 is greater than 6 and 6 is greater than 5. So we can decide that the peak element will come in this side, not to the this side. So we can directly ignore this part and we will only check the left part. Okay, so same things we will repeat on this part. So that means we have removed half of the space, similar to the binary search. Now we will check the same things on this part.
Sir, what if in the list, in place of 3, there is 10, sir? Then
Where?
in the list, in place of 3, we have 10. Then we cannot skip the other part. So.
No, so what you are saying, we have like this 1, 10, 9, 8, 7, 6, 5, 4, 10, like this?
Yes, sir, 10 or 11, any higher number.
Okay, higher. This you are saying that this is a 1. So then this is the violation of the problem statement. So here 2 peaks are there. Okay, so this is also one possible peak. This is also one possible peak. Okay, so that is not possible. Okay, according to the definition of peak, if any elements is greater than to their neighbors, so that is actually peak. But only one peak is possible in the input. So this is not the possible input for the problem statement.
Yes, sir.
Okay, So only that three conditions are possible for the input. So just write the logic for that. So any one of you have done?
Yes, sir.
Okay, so just tell me your Replit ID. I'll share your screen and then you can explain your code.
Okay.
1 second.
It's Nitin Reddy, sir.
Okay, I'm opening. Yeah, Nitin Reddy. This is problem 2. Okay, you are solving problem. Okay, this is the one. Okay, so yeah, this is your code. You can explain what you are doing. Can you just quickly explain?
Yes, sir. I did it in two ways. First in recursive way, and this one is with iterative way.
Okay.
So while I submitting in recursive way, one of the test case didn't pass because of maximum recursions, I think. This
Okay.
way is by iterating. I have kept two variables low and high, which points the ends of the list, and the middle element points to the mid of the list. First two conditions are to check the extremes of the list, which is L of 0 and L of 1, and the other in L of -1 and L of -2. If these two cases didn't pass, the condition will go to the next if statement, which checks the middlemost element. If it is greater than the neighbors, it will return the L of mid, or then it will check if one of the neighbor is more than the mid, it will the lower element is set to the mid plus 1, so that the loop checks the second half of the like binary search. It works
Okay,
as a
okay.
binary search.
Okay, you set your that low pointer to the mid plus 1. So that means you remove the left part.
Yes, sir.
Here you remove the right part.
Right part.
Yeah, correct. So this is the correct implementation. Let me check this on the portal. Okay. So is this passing the test? Yes. Okay, so you can see the private test case are passed. Let's see the public test case also. Yeah, all public test case are also passed. Yeah, this is the efficient solution. We can see that, because if we compare the recursive implementation or iterative implementation, then iterative implementation is more better. Okay, because that recursive overhead actually reduced in this iterative things. So if you know the iterative solution, then prefer to write the iterative solution. Do not write the recursive solution. If you don't know, then try.
Okay, sir.
Okay, yeah, this is nice. Okay. So anyone have any doubt in this implementation? Any query? What logic we have discussed, and so same things we have implemented here. Okay. So any query in this solution? And one more thing, I
Yes,
hope you know or don't know, that Replit team will be removed from to the 1st August. Okay, so this feature actually Replit will remove. So also just after solving the questions on the Replit, please also save your solution on the portal. So maybe after 1st August you will not get the problems on the Replit team. Okay,
Sir, I have a doubt.
Yeah.
Do we have to the first statement, first if and the second if, we have to use it inside the while, or we can use it outside the while also?
So you are saying that yeah, you can also use this outside of the while. Okay, so this is one time. Actually, this is the one time condition. Actually, you can check.
Sir,
Yes.
sir, can you explain the third elif statement, like on which basis that will happen?
Okay. Okay. One second. So let me just write this. Okay. So if this, elif this, and I change this to if. Still all test cases are passed. Okay, so this condition is required only to check one time. So you can just write one time. Yeah, that is also one improved version.
Sir,
Yeah. So yeah, someone is asking this LF part, this part. Yeah.
It's a
Yeah, what's
condition.
Okay, so I've written this condition here. So what we are doing, the same things which we have discussed. So what can just check the first condition what is written. So L mid, if L mid is greater than, so that L mid. Okay, so this middle index element we are checking. If this is greater than L of mid plus 1. Okay, and same times we are also using the one another condition with AND operation. Okay, so that means that should also be fulfilled to check this condition. Okay, so what we can check, if L mid is greater than 2, so that means we can write like sign this. Okay, so L mid minus 1. Okay, if above two conditions are not satisfied, then we are going to this condition. So this is the, if this condition is true, if this condition is true, so that means our peak elements is the middle element. This mid element is the peak element, because this is the, this condition will only be satisfied at for the one element. So that is actually a peak element in the list. If this condition is not true, so we will move to the second condition. So second, what is the second condition? So what we are writing, this L mid is smaller than L mid plus 1. Okay, so we are just changing this condition L for this. So L mid is lesser than L mid minus 1, mid plus 1. Okay, so this is the mid. Okay, so if this condition is true, and only this, after checking this condition, that means any one condition is failed in this, either this one or this one. So if we are, then we are checking this condition. So if L mid is smaller than 2 L mid plus 1. Okay, so this value is smaller than mid plus 1. So that we can say that our larger element will come to the this mid plus 1 side. So we can remove the left part. Okay, or what you can do, if you this single condition, if you are not able to understand, but you can write the complete condition. Okay, so here some inheritance is there. So what you can do, you can also write like this. So if this, you are getting this L mid minus 1. Okay, so you can write this complete condition. Okay, so here what happened, actually, if this condition is not true, then you can check if our elements order are going in this way. So that means our elements are increasing in increasing order, and you are lying in this area. Okay, so that means our peak element will come to this side after mid. Okay, because our elements are increasing to this side, so maximum element will come onto the right side. So what you can do, you can just skip the left part completely and set your low value. So low index and right index is actually the index to which decide that which part we will check in the next iteration. So here low index you will set to the mid plus 1. So low you are setting to the this position, and high is already set to the last index which is used in the previous iteration. So that means you have ignored this complete part, what is coming before that, and you will check to the only this part. If this second condition is not true, that means only the one remaining condition. So you can write, use only else part for that. So that condition is actually L mid is greater than L mid plus 1 and greater than this L mid minus 1. So this condition. Okay, so else condition is actually satisfying this condition. So if elements are coming in this order, so maximum element will come this side. Okay, so that means you can skip this left right part completely. Okay, and next iteration will check the left part only. So because of that, we are deciding our high to mid minus 1 here at this pointer. So this will this high, and lower will remain the previous what lower we used. So that part we will check in the next. Okay. So in this way, this implementation is working.
Sir, I have made a code like, but I have made with like only with similar with limited conditions. Like I didn't had like I understand the logic of this code you are presenting, but I didn't make a lot of
Okay,
conditions.
so
But
just tell me your replicate name.
yeah, DEVAKKASH.
Okay, 1 second. Okay.
Yes.
This simple way. Okay.
I think that is.
This is the one.
Yeah.
Yeah. Okay. So
Sir,
find
just
peak.
to check if all of our cases are getting passed.
Sorry.
How to check if all of our cases are getting passed?
So you can just use that. You can okay. So on the replit, you can check this test things. Okay. So where is unit test? There's one unit test option, and inside this unit test, okay, the test case are not there. 1 second. Okay, yeah, test option is there. So tests, and you can check this run test button. Okay, so here some test cases are there. Maybe these test case will pass, or you can see the test case. If but you can also validate your code on the portal. Okay, and check that your code is passing the last test case or not. Because here we are not using any validation operation. Okay, so here you will get, if you write the answer like this, return max of L, still here your test case will be passed. These test case will pass actually. Okay, but on portal efficient code is required. Okay, some that prefix validation code is there on the portal. Okay, so regarding this code, this is no, this one, yeah, this one. So and left, right 0 and n minus 1. Okay, while left is less than equal to right, left plus right divided by 2. If L of mid is greater than L of mid plus 1.
Sir, I just reduced the boundary. That's it. Like stored the value of the higher in the right, and then I started reducing the boundary.
So is this working fine?
Yeah, I guess.
Yeah, I think it will. I think it will work because I have seen this code also. So I have seen this code also, because this is also fulfilling the all cases.
I was at start. I was failing the test
Because
cases. Later on,
complexity wise, this is okay.
Okay.
What is this? Okay, fine. Okay, some name. I can find peaks.
So in while condition, there is only lesser than. There is no equal sign. I think that is making some mistake.
First thing, some function name. Yeah, okay, fast. Yeah, so yeah, this is also working. Okay, so here complexity wise this is okay, because this is log n concept, but by this condition also it is fulfilling all the cases, corner cases. Okay, you can also just try to take some more cases, because I have also found that this code is working fine, because in at the last it is reaching at the maximum element. What we are doing, actually we are just based on the condition, we are checking if a mid element is greater than the mid plus 1, then we are shifting. So similar to the binary search concept. Okay, so because we have max element in the list. Okay, so there is no chance our element is not exist in the list. So definitely maximum element will be there, either on any corner side or any middle side. So what we are using here, we are searching the max element. So we are shifting our position in this by this condition. So L mid is greater than mid plus 1, then we will shift our right to mid, and else otherwise left to mid plus 1. And in last, when we will reach, so this condition will become false, we will return the L left. So this will also reach to the maximum element. Yeah, this is also correct. But here you have to just apply the dry run to understand this code in the better way, how this is actually reaching in the always. Okay, yeah, this is also fine. Okay. Okay, any query in this first solution? Then we will move to the second column. Okay, so let's move to the second. Okay, second problem, you can see, write a Python function, find common elements L1 and L2 that accept two integer list L1 and L2 of same length n, and return a list that contain elements that are common to both lists. Write a efficient solution that runs in order of n log n or order of n time. Okay, so here two complexity are mentioned. So just figure out that by which approach you can achieve the n log n time, or how you can more improve this approach to the order of n time.
Sir,
By sorting.
by giving actually like n log n is like an int. You can use binary search for each element for n elements, then you can get n log n, I guess.
Okay, so what you are saying, you can sort the list. So you are sorting both
then,
list.
No, so like if you take an element in list 1 and we are keeping that as target, and we are checking that in the second list and using binary search.
Okay, so at least so you are saying that at least once list is should be sorted in the sorted order, then you can apply binary search. No?
It's one
Hmm.
at least one list is sorted.
Yeah. So what you can do here, no need to write the complete sorting algorithms for here. So like no need to write this that merge sort or quick sort things. So you can use this directly, this Python sort function. Okay, so by default this Python sort is also provided this n log n time.
Sir, but they are given that do not use Python Boolean functions.
No, if function is if you are getting the correct complexity by the built-in function. So I said that some function actually takes some time. So like in the previous operation, slicing operation, which is taking order of n time, but you are writing a solution for log n time. So how you can achieve the log n time if your one operation is taking order of n time in your code? Okay, so because of that, I said that just if you are using any built-in sort, built-in function, so just also you should know that how much time actually that built-in function is taking internally. Okay, so by default, this built-in sort function actually takes order of n log n time.
But sir, if we want to do it like all the first principles, first we have to sort, then we have to compare each element, right?
So yeah, after sorting, what is your approach? So actually, we have two list here, L1, okay, and L2. So you are saying that sort one list, because both have n element.
Lists.
Okay, both lists.
Yeah, sort both the element, and because they have the same n elements, so
No.
it should be same if it's sorted.
No, elements are not same. Size is same.
Okay.
So
yeah, the size
actually
will be
there's no
same,
need to sort, right? There's no need to sort. Just take list L1, go through, iterate through the whole list, and then use the binary search function on L2, and if that element is found, append it to the
No, but it is not. But it is not mentioned that these lists are in sorted order.
But
Sir,
why do you need a sorted order? Why do you need it sorted? You're just trying to find the common element, right?
So, but how you can apply the binary search if list is not sorted?
Sir,
okay, then you can sort the second list and then use the binary search.
So that times what you are saying, another one. Okay, I'm not.
Sir, I have another approach.
Okay.
Like, what if you use the merge algorithm, like the two-pointer algorithm?
Yes.
If we check on both the elements, like while sorting, like if we take two elements are equal, then we can append it to a list. Like there's no need of sorting for separation.
Okay, then what would be the complexity for that merge operation?
So, yeah, it will be n, I guess. Like both the elements, both the lists we are iterating at the same time. So, like it's the merge algorithm.
But that merge operation, you can apply if the list is already sorted.
No, so like it can.
So you are
like
saying
we
that
can
like
pick the
if you have
sorting time.
No, suppose we have element like this, so 3, 5, 2, 1, 8. Another list we have like L1. This is L2. Another list we have like 5, 4, 1, 6, 7, like this. Okay, all these lists are not in the sorted order. Okay, so both have the 5 elements. So
okay, sir. Okay, we have to sort it for. Okay, I forgot that.
Okay, so merge operation actually works on the sorted list.
Yeah, we need sorted lists. Okay.
Yes.
Sir, we can do this problem in big O of n, sir. Like
How?
by converting one of the list into a set and searching the element. Like for converting one list into a set, it takes big O of n, and searching from a set, it takes only big O of 1, no, sir. Searching element from a list.
So how you know that searching in the set takes order for constant time?
I searched it, sir.
Okay, so searching operation takes constant time in the set, you are saying?
Yes, sir. Because every element allocates is being allocated a memory in a in the memory, sir. So
do we have indexing in the search?
Yes, sir. Yes, sir.
What operation? Really? So set. I am not sure that set have the indexing.
Sir, set does not have index, sir.
Sir, every not indexing, sir. Every element is sorted into a memory, sir, individually. So taking out of the memory takes only big O of 1 in a set, sir.
Okay. Yeah, you are going in the correct direction, but here set actually that searching. I'm also not sure about this. That search what actually internally happens in the set in the Python. So how it actually provides the constant time. So let me search the searching time in Python set. Time for the search operation, the Python set is typically constant on average. Okay.
In the lectures, sir described that the set takes less time to retrieve any element because it takes more memory to store each element.
The one time the searching the achievement because sets in Python similar to the dictionary stable because searches can be scenario where hash collection. Okay. So the set is actually also use the same hashing concept which actually dictionary is also used. Yeah. Okay.
Yes,
So yeah. So I am also not aware of the set internal things because generally we not use the sets. Yeah, dictionary. If you know the dictionary, so dictionary concept is actually we know that dictionary is implemented with the help of hashing concept, and this dictionary concept you will learn in the big three topics. Okay. So instead of this set, what you can do, you can use the dictionary. Because we are not sure about the set things, but dictionary we are sure about that because dictionary is implemented with the help of this hashing concept, and hashing concept basically provide the constant time for searching and storing the data. Okay, so any key in the dictionary can be searched in the constant time. So yeah, you are correct. So if you are saying that if we can make set for one list and we search the element from the second list into the set, so you can get the common elements in the order of n time. Yeah, it is correct. Okay, same things we can do with the dictionary. You can make the dictionary for first list and search the element from the second list elements into the dictionary. So that will also take the constant time in searching. Okay, then you can also achieve the order of n time. Yeah, this is also fine. Okay, yeah, this approach is correct. Okay, so what is the naive approach if we solve this problem by the naive approach? So what is the naive approach if anyone is don't know the sorting things and this constant time things? So what they will do actually, L1, L2. So they will take the elements one by one. Okay, so first element from the first list and directly apply the search operation to the second list. Okay, if list is not in the sorted order, it will take order of n time. So total we have n element in the first list. Okay, so we have total n elements, and same we have n elements in the second list. So each element will take n time to the searching. Okay, so total time will become n square if we are following this naive approach to find out the common elements. Another approach to improve this version is if we sort one list. Okay, so L1 we apply the sort. Okay, and we iterate the L2 list one by one, and we will check the each element from the L2 and apply the binary search and check in the L1 using the binary search. So each element will search in log n time. Okay, so we have total n element and each element is taking log n time. So that means the total complexity will become n into log n. Okay, so this
so
is
sir,
one.
From the list, we send a element to the list 2 and then we'll search it.
Sorry, what you can you repeat?
An element from list 1 would be sent to list 2 and will be sent to the binary search and we'll check for list 2 there.
Yes, you can pass the L1 list, which is sorted actually. That you can pass that sorted list to the binary search and pass the element from the another list. Suppose if you are checking the first element and L1 is already sorted now. So check this element is exist in the L1 or not with the help of binary search. Okay, in L1.
So what is the first approach you told, sir?
No, first approach I explained the naive approach actually. Suppose if you have random element L1, you have like this 3, 4, 5, 2, 1, 6, 9, 8, like okay, and another list L2 you have like 3, 6, 8, 7, 4, 10, 13, 14, like okay. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So what you can do, naive approach is saying that you can just read the element one by one, this 3, and just check 3 is exist in the list or not. Okay, so L2 or not. So you can operation you can check if 3 in L2. Okay, then you can write this is the common element. So this in operation by default, when you use this in operation, by default this operation is order of n operation. Okay, this is also required. If you are using this in operation in to check in the list, that operation or internally take order of n operation because it performs the linear search. So it will take n time for this. Okay, and similar for 4, you will check the 4. What 4 is exist in the L2, you will perform order of n time. So in this way, it will take order of n square. Okay, another method is you sort the list. You can sort L1 or maybe L2. Suppose if you are sorting L1, so L1 become this like this: 1, 2, 3, 4, 5, 6, 9, 8, 6, 8, 9. Sorry. Okay, and L2 will remain same. No need to sort L2. 3, 6, 8, 7, 4, 10, 13, 14. Okay, now what you can do, you can just pick the element 3 and just check this element with the help of binary search in this L1. Okay, 3 is exist in the L1 because here this list is now sorted, and sorted operation actually takes order of n log n time. Okay, so this order of n log n time is required for sorting this L1. After that, each element is searching in order of this log n time in this list L1. So you have total n elements that will also perform by n log n. Okay, so these two operations are actually performing sequentially. After this operation, you are performing this operation. So overall complexity will remain n log n. Okay, so in this way you can achieve the solution in n log n time. The last approach, you can use this, you can create a dictionary for one list. Okay, so what you can do, you can create a dictionary for L1 lists. So dictionary is like this, you have created dictionary, so you can make key for every value. Okay, so like this 3, because all value are distinct in the one list, so you can pass any value for this, like 1. Okay, similar for the 4 and for 1 5 1 2 1 and 1 1. So this is actually key, and this is correspond value. So value we are just assuming 1, and 6 1 9 1 and 8 1. Okay, so this is now dictionary created. So this dictionary creation operation will take order of n time. Okay, we will just traverse all the elements one by one, and we will make a key in the dictionary. So this operation will take order of n time. After that, what you can do, you can simply just apply this 3 if this 3 in D. Okay, so in this operation 3 in D, it takes constant time. Okay, you can search the key in the dictionary in constant time, because this is implemented with the help of hashing concept, and this hashing concept will is discussed in the week 3. Okay, so just wait for week 3 concepts, and you will get the idea how this searching happens in the constant time with the help of hashing concept. So this operation take constant time, so every element you can search in constant time. So that means n elements you are searching in n time. So n time is required for the searching operation. So overall time, first this order of n is required for the creation of dictionary, and order of n is required for the searching for each element from the L2. So overall time, so this is the total separate time. So we go order of n plus order of n, that means overall order of n. So this is the more efficient way. So here actually we have changed the data structure. So this is the example of the data structure, how we can improve the our complexity or time efficiency if we change the data structure. Sometimes data structure also help to improve the complexity. Okay.
Sir,
yes,
here we are using dictionary because of hashing. Means it is because of that only, right?
yes, because the searching time is actually constant in the dictionary.
So like I have another approach.
Okay.
Like I've used collection library. Like if we use we are taking here n because we are setting the values to the keys, updating one by one. Like for example, if you use the collection and if we make the initial of all keys as 0, and once if we encounter more than once, then like we can directly append it to a list. Like
no, what you are I'm not sure about this collection things. So collection, what you are trying to do with the help of collection, you are creating dictionary, na?
Yes, sir.
So
yeah,
definitely it will take out of n time if you are creating dictionary. So that means you are making the key for every elements from the list.
Oh, okay.
So that means you have to need traversing for the each element from the list, and you will create a dictionary. So that collection, if any shortcut is there, that shortcut is actually will also take order of n time, because iteration is required for the each element. Okay, so internally it will take order of n time. So if you're using any built-in things.
Sir, one question I have. How do we know that like which value of complexity is less, like order of n or n log n? How do we know that?
So this you can so this you are saying that this n square is greater or n is greater or n log n.
Log n, yeah.
Yeah. So this is okay.
So it is available on the GitHub notes.
This is available in the
Yesterday
GitHub.
on
Otherwise, you can simply assume that. So if what is the smallest things? This is one. Okay. If we write like log n, this is the next increasing level. Or we can also write after this. There is one more is square root of n. Okay. And then we can after that we can write generally use this n, then n log n. Okay, and then we can also sometimes we also get the complexity n log n. No, that is actually better than this. Okay, so log n or sometimes n log n, then n square, then n q like this. Okay, so n to the power. Uh, so this is the or so n to the power k we use, and then to last is 2 to the power n. So this is the order of in the increasing order. So these are the very common complexity we actually generally got for the code.
How can we calculate complexity on our own? Like you just said, you wrote a code and then you understood that okay, this will take this value. Or I mean, so how do we know prior these things?
Okay. So that actually we decide based on the code. So inside the code, if our code only contains the iterative things, okay, our code is not a recursive code. Okay, so then we decide our complexity based on the iterations. Okay, so suppose in the this code, like this, what we are saying, this approach actually. Okay, so where we are sorting the list. So here L1, if we are sorting this list, L dot sort. So this sort function basically used any efficient approach. In Python, there is some what algorithm name is, but that is actually used the combination of merge sort and insertion sort. And some name is also mentioned of that sort. Tim sort. No? Oh yeah, Tim sort. So that is actually also a order of n log n complexity. Okay, so this complexity is defined for the sorting. If you have learned the merge sort and selection sort, that quick sort, you know that how we are getting this n log n. But okay, but apart from that, if you are iterating any list, suppose this L1 list, if you have n elements and you are running a loop like for I in, so I in L, okay, and you are performing something, some operation, constant operation. Okay, so that means you are iterating each element of the list one by one. So that means if we have n elements, so this in an internal operation will perform n times. Okay, so actually we figure out that how our operations are depends on the input size. Okay, based on that we decide how. So based on the loop, we decide that our loop will run n times. So here what we are considering for the input, we are considering for the input is the size of the list. And if we are only iterating this list one time, so that means it is taking n time. Suppose what happened if we are writing like this. So if so for I in, so like in the bubble sort which we have discussed in L, and inside this loop we run another loop. So for J in L like this. Okay, so this is len of L. We can say len of L, and this is len of L. So and then we are performing some operation here. So this operation is basically constant operation here. But how many times this operation will perform? Because every value of the outer loop, okay, this loop will completely run for n times. Okay, what is the size of list? Okay,
how did you know that this is like constant? You are assuming that let's have a constant order.
No, I'm not assuming. So that will decide on the code based. Actually, let me just open any code. Okay, so we discussed this bubble sort. Find search. Okay, I'll remove. Let me open the summary documents. Some codes are there. So that actually we decide. So here you can see Okay, so in this code, in the above code, you can see we have just considering this code. Okay,
Yeah.
and here this outer loop is running for the n time. Okay, what n is there, we have just mentioned here. So if n is any input we have, here is this is the another loop, and inside this there is one simple expression.
Simple expression.
Okay,
Yeah.
so this expression will take constant time if it is written only like this: a equal to 10, b equal to 10. Here this is a constant, will take constant time operation. But if this expression is coming under the loop, so that means for every value of I, this part will run n times. Correct? So this instruction will also run n times for single value of I. And we have n value for I. So that means this part will run n times, and so overall will become n square, n into n. Okay, now you can see this code. If you have this type of part in your code where you have 3 nested loop, so this is taking order of n time, but it is running for n values for this, so it become n square. Now it, for every value of I, this part is taking n square, so that means for n value it will become n cube. Okay, so like this is the one combination of the code. Okay, so here actually we have different blocks of the code. So after finishing of this part, then this part is
So shall we add the complexity in this case?
So what we will do, we can just calculate the complexity code wise, block wise. Okay, so what is the complexity for this part?
N.
And what is the complexity of this part?
Again, n square.
N square. What is the complexity of this part?
N cube.
Okay, so in this case, we takes the maximum.
Okay.
Order of n cube. Okay, so in this way, so this is the iterative code. If you have the iterative code, there's no recursive call like this. And we have a different approach to find out the complexity for recursive approach. Actually, okay, we cannot calculate. Actually, we need to find out that how many times recursive calls has actually happened if we are using any recursive solution. Okay, so in this case,
on this recursive calculation a little more.
Okay, so first thing, we use the recurrence relation. And what is the meaning of recurrence relation? Let me explain. So for recursive solution, we need a recurrence relation. And after that, we can decide the complexity. So suppose this code, okay. So here, this is a code of the factorial, and we are using the recursive function. So what is the recursive function? If we have the input n, okay, so we write the total time for input n, tn. Okay, so this is representing a total time for n input. But when we are calling this complete function, so we check what part actually we are implementing, and what are the another part of, so there is actually two part, some computational part and another is recursive call part, where we are calling the same function again. Okay, so that function actually we have here. So return this n into this part, n into, okay, factorial. So that means we are calling the same function again. So we can write the recursive relation here like this. So t, so that means this is also a new problem. Okay, so like this main problem, this is again a same problems, but the input is changed here.
-1, yeah.
Okay, so what we can do, we can write n minus 1. So that means we are writing this total time is equal to the time of this recursive call, and plus what other than this recursive call, what our code actually, what is the complexity of our remaining code. Okay, so what complexity, what operation actually we are performing apart from this recursive call. So we are performing one if condition, this is a constant operation, and we are performing this one multiplication, so n into this fact. Okay, so that operation is also a multiplication constant operation. So we can write like 1 here. Sometimes we write like tn minus 1 plus order of 1. So both are the correct way to represent this recurrence relation for this. So this is called as a recurrence relation for the recursive code. So after getting this, we can calculate the complexity with the help of this recurrence relation. So this is the example. First, you should know how to write the this recurrence relation. Okay. Now you have already seen this merge sort.
Here, one thing like constant thing you are just taking as in one form only because matlab one if that constant and then n into means taking any one constant value.
So one
Means
means I'm not writing the number of operation here.
Yeah,
If
yeah.
your code is taking constant time means that is not depends on the input. Okay,
Okay.
that means if you are getting any value of n, this number of instruction will execute fixed number of time. Okay, if you are getting suppose 4 instruction are executing, 5 instruction are executing, that are actually fixed, and it is not depends on the input, that are not changing based on the input. How many times that number of that instructions are executing, that is not changing based on the input. So that we called as a constant time, and we write as a 1. Okay, or bigger one this time.
So here, but sir, we are saying that n when n is 0, so that means it is dependent on the input, right?
No. If suppose if you are getting, this is a conditional statement.
Yeah, yeah.
If any value of you are getting n equal to 5, okay, still this condition will be checked only one time.
Okay, yeah.
Okay, so this statement will always execute one time. It is not depends on the value of n.
Okay, yeah.
Okay, so here we are just checking
We
how many
are
times our instruction
how
will
many
execute.
times any instruction is being, that is what
Yes.
complexity means.
Yeah. Okay, so because we are writing this, okay. Now let's discuss the complexity of merge sort, because merge sort we are also using the recursive approach. Okay, so then we will understand. So here you can see this. Here we have written.
For the factorial one, what is the complexity then?
So here I'll explain the complexity later, but let me explain the recurrence relation first. Okay.
Okay.
So this is the one example. Let me discuss this. One second. So yeah, meanwhile others, please try to solve the problem number 3rd and 4th. Okay, so we will discuss after this. Okay, so here what happened, actually this part we have written for the merge sort. Okay, and we have skipped this. We have another function for the merge sort. This is actually merge. Okay, so this is the another function, and this is the recursive function we have. So if you see this code, this recursive code, so how we can write the recurrence relation for this? So we can say that what and actually what input we are taking here, we are taking the input size of the list. This A is actually a list which we are sorting. So if suppose the length of this list A is n, okay, so here this we are using n, and we are calculating the complexity Tn. Okay, so Tn is the, then we will write, okay, just check this this part. Okay, so this is a single constant operation, this part is also a constant operation. Okay, this is conditional statement, but here this is a recursive call. Okay, and this is also a recursive call, and both recursive call are performing half of the input. You can see n by 2. Okay, so initially we are performing the same call on the full list, but internally we are calling the same function 2 times on half of the input. So that means this is the recursive part, and we can write we are calling the same function 2 times 2t. Okay, and what is the input size we are giving to this? N by 2. So we can write like this, n by 2. Okay, so that means we are finding out the complexity of this part. So here we are writing like this, 2t and n by 2. This is the time for this recursive part. But apart from this part, what is the complexity of the remaining part? So here we have checked that this is a constant operation, but here there is one function, merge function. Okay, this merge function, what is the time for this merge function actually? Because here we are getting the list with half of the elements, so n by 2 element. Okay, and this list also contains the n by 2 elements. Okay, and these two n by 2 elements we are passing in this merge operation. Okay, and this merge operation actually is a operation that merge two sorted list. So that means you know if you know the merge code. So let me open the merge code. Okay, insertion sort. Yeah, this merge sort. Okay, so here actually this merge sort is the same, this part. Okay, and this is the merge code. Okay, sorry, this one. And if you see this code, here we are getting two input, A and B. So this is the list with n by 2 elements and n by 2 elements. And after that, we are simply running a loop, while loop, and this loop is running for the m size. So if I is less than m or j is less than n, so this m and n are the size of the A and B. So most of the time, this size is actually equal, n by 2. And we are simply comparing the element because both lists are sorted, and we are comparing the elements, and we are just shifting the elements into the new list.
Sir, I have just have a slide out. What is the time complexity of the append operation? Is it constant or-
Append operation is the constant. Okay, so what happened actually? Append operation insert the new element at the last. So there is nothing happens with the remaining elements. Nothing operation performed with the remaining elements. Only just one new element added to the last at the last position.
Yeah,
and
okay.
one new index is assigned for that. So only single operation is performed. So that append operation take constant time. Okay, so this operation actually what we are doing, we are simply traversing two lists with the n by 2 size. So after combining the both lists, it will take actually order of n time. Because if you suppose if you have two lists, like a list you have, and here elements are 1, 3, 5, 7. Okay, and I'm just writing the worst case situation. Okay, so 2, 3, 6, 8, like this. Okay, so 1, 3, 5, 7, 2, 3, 6, 8. So these are the two lists. So to merging these two sorted lists, what will happen? Actually, we simply compare the elements, first element. Okay, so which one is the smaller? This one. So we will just pass this smallest element into the sorted list 1, and we will move our pointer to the second element, which is actually passed. So then now we will compare 3 and 2. Now which is smaller? 2. So the 2 will pass. Okay, now pointer will move to the next element in B. So now 3 and 3. So okay, so 3, 3. Then we will pass the A list. So let me just discuss this 4. It is more clear. Okay, so 3 and 4, the 3 will be passed, and okay, now this 5 will compare with, then 4 will be passed. Now pointer will move here, so 5 will compare with 6. Now 5 is smaller, 5 will pass, and now we will move to the 7. 7 and 6, 6 is smaller, 6 will move to this, and then 7 and 8, 7 is smaller, 7 will move, and then 7 and so 8 is remaining, so 8 will move. So you can see how many comparison we are performing in this element. So we are simply compare one by one. Okay, so this 1 with 2, then 1 is moved, then 3 with 2. So we are traversing all elements of the A and all elements of the B, and these are n by 2 elements, these are also n by 2 elements. So that means we are traversing n elements. Okay, so that means overall complexity required for this operation is order of n. Okay, so this means merge function complexity is order of n. This
So, aren't we like adding all this, and will that come to value of n? Like,
yes, yes.
Part wise, what you have done. So part wise, if we calculate the complexity, so will that again come to be n?
Yeah, this will come. This is the worst case situation. Then you will get this because you need the iteration of each element of the both list. You want to compare. So that means we have total n by 2 plus n by 2, total n elements. Okay, so that means overall complexity is required out of n. That means n iteration is required.
So in current code, what you are showing?
So that codes. Now we have figured out that what is the complexity of merge function.
Yeah.
Order of n. So now you can see, apart from this recursive part, we have a function that call this merge. We are calling. This will take actually order of n time.
N times, yeah.
So that time we will write here order of n.
Okay.
This recursive relation. So that means this tn is the total time which we are calculating with the help of this recursive part time and the part which actually not contain the recursive call. Okay, so this tn is actually equivalent to this this time and plus this time.
And also will have a constant value also, right? Or
No, the constant part actually we not written if we are getting any higher part. So regarding the complexity, so apart from this code, if we are getting the complexity of this part, this is order of 1, and this part, this is order of n. So we pick the maximum for the overall. Okay, we will not write like this. There is no meaning for that. Okay, so we ignore this. So this is the recurrence relation for the recursive solution. In this way, we will calculate the recurrence relation.
So
And
basically, a number of times any instruction is being executed, that we have to figure out, and
yes,
that's
so that relation actually you have to figure out that based on the input value, how many times. Okay, and after getting this recurrence relation, then you can use some method to expand this. So in the previous example, when we are getting the recurrence relation like this, so Tn equal to Tn minus 1 plus 1. Okay, so how we can expand this? So we can simply create the equation for that series for this. So if we have Tn, we are getting Tn minus 1 plus 1. Now this is also a problem. Then what we can replace this? Tn minus 2 plus 1. Okay, so this part we can replace. Okay, plus 1. So this is coming from here, and this part we have written. Okay, now again, then we can replace this with Tn minus 3 and plus 1. Okay, so this part is replaced. Now the 1 is coming from here and 1 is coming from here. Okay, so in this way we are getting 3, and we are just moving to n minus 1, n minus 4, and at one time we will move to the 1. That is actually the base case of the recursive solution. So at any point we will reach like this. So T 1 and plus we have 1. In this way we will get n minus 1 times. Okay, so this one actually, and when we are watching this, when we are reaching this T1, so that is actually base case. So that will take constant time. So this is actually representing this base case situation in the recursive solution if n equal to 0. If this condition we are reaching, so this will take constant time. So here we will directly replace this 1. Okay, so now we have total 1 plus 1 plus like this n times. So total n.
N. Correct.
Operation is required. So complexity will become order of n. Okay, so this is for that factorial one. But for the merge sort, okay, so where we have the recurrence relation like this, Tn equal to 2Tn by 2 plus that n. Okay, so that expression you can also expand in the same way. If you know this, and after that you can figure out the series and then you can calculate mathematically. Otherwise, we have some method that we will discuss in the week 8, that is actually recursion tree method. Okay, that is actually helpful to calculate the complexity of this type of recurrence relation. So what happened actually, we have initially Tn, okay, and for this we are calling 2 times, okay, this Tn by 2, Tn by 2 and Tn by 2. I am just drawing this hierarchical structure, okay, and apart from this we are taking this, okay, so this is Tn by 2 plus n. Okay, so this n is required. So okay, so we will not write this. Okay, so we will just draw the recursive call structure with the with this how we are calling. Okay, so apart from this calling, we have the constant time n. Now this is the new problem. Okay, these are the 2 new problem for this. So if we have Tn, our time is required n. If we have Tn by 2, what is the time required? N by 2. Okay, and same for this n by 2. Okay, so total time is n by 2 plus n by 2. This will remain total n. But again, this will call 2 times. So Tn by 4 and Tn by 4. Okay, this will also call 2 times. So Tn by 4 and n by 4. So in this way, our problems are actually expanding and our size is reducing every time. But here, if you have, if input is n, you are getting the time required for the merge part is n. If input is n by 4, time is required n by 4 for this part. Okay, n by 4.
4 times n
For
by
this n by 4. So 4 times. So 4 into n by 4.
again n.
So again n. So that means at each level,
Hmm.
okay, you are getting n now operation. In this way, you will just expand this, and at one time you will get t1. Okay, after dividing multiple time, you will reach the condition n by n, and you will get t1. Okay, so at that time t1, all last level actually of this tree, you will reach t1 n times.
Again n.
Okay, so 1 for each. So then you will get n times.
Mhm.
So now each level you have n time, and
And
how many levels? How many levels are possible for this in this way? So every time you are dividing by 2. So how many levels are possible? Okay, so initially you have n, then n by 2, then n by 4.
So this is log n
So
times,
how
right?
many levels? Yeah. So you will reach from this n to 1 in log n time, log n steps. Okay, so that means you have log n levels, and each levels n time is required. So total time is required n log n.
Okay.
Okay, so because of that we are getting complexity below n log n for this. Okay, but we will also discuss the another way if suppose this is not same at the each level. Okay. Suppose if this is decreasing or this is increasing at the each level wise, so how we can decide the complexity? So some formula is mentioned, so that we will discuss in the week 8. So you can directly calculate the complexity based on that for the recursive solution.
So, sir, what is the real-time understanding like for optimization of code? Means why are we considering the complexity and all?
So because of that, just improve the efficiency, time efficiency. So we compared some sorting algorithms. Okay, why we discuss these 4 sorting algorithms? We discuss selection sort, then insertion sort, then merge sort, then quick sort. Okay, because these selection sort is taking out of n square. This is also take n square in worst case. Merge sort is taking in each case n log n. Okay, quick sort is taking in best average case n log n, but in worst case it is also taking n square. So which is better actually? Purpose is same for the each algorithm. Okay, we are sorting the algorithm, we are sorting the elements. Purpose is same, but which is fastest? So definitely merge sort is better than the selection sort, and n log n time is much better than the n square. Suppose if this input is very large, suppose you have this input is like 1000. Okay, if you apply the selection sort, it will take 1000 to 1000 time. But if you suppose if you use this approach merge sort, it will take 1000 into log n. So what is the log n? Is near to 10. Okay.
Time decreases.
Yeah. So this is very efficient compared to this. So generally we compare the efficiency on the large input actually. For the small input, that will not reflect actually, but large input you will get much difference. Okay, so this n log n. So this n log n is much better than the n square.
Okay.
So because of that, we improve our code efficiency. Suppose if you're developing any application for a specific purpose, okay, and you have 2-3 separate developers, and you are all are writing the same logic for any purpose, okay. But if your code is not efficient compared to the other code, definitely other person code will be used. Okay, so this is required things to make the application fast, make the process fast. Like
Optimize.
Yeah, optimize things.
Okay, thank you.
Okay. Yeah. Okay, so let's move to the problem number 3. So can just discuss. So I hope this problem 2 is clear. This is not too much difficult. Only the searching and sorting things is required.
Sir, I have some doubt in problem 2, like just a clarification. Like if we can attain, like you said, if you use dictionary, we can attain the linear time. But like if by using dictionary, doesn't it affect the space complexity, sir?
Yeah, it will increase the, yeah, correct, it's space complexity. Yeah,
So,
that
Sir,
is so that is actually a trade-off in the space and time complexity. If you use the additional space, you can improve the time complexity. If you reduce the space, that time complexity will be increased. So if most of the time we more focused on the time complexity, because right now we have the enough space things, so that space is not too much problems, but yeah, time is the main problems actually which we want to improve. So yeah, if space complexity is increasing in this case.
sir, and also in operation in dictionary is constant, right? That's what you say.
Yeah, that is constant operation. In
Yeah. Okay.
operation takes out of constant time.
Sir, for the second one, my one of the private test case is not passing.
Okay, second problem.
Yes.
Let me open your report. Okay, now
I did the dictionary method, but
Mhm.
this
What
something
is your? I'm not able to figure out your replit ID. Can you tell me your
NAGLA, that one.
replit? NHJ.
Yeah, that one. Below Atul.
Oh, this one. Okay.
Yes.
Where is your code? You haven't
Oh,
written
I
the
did
code.
it in. Okay, I'll paste it in.
Yeah, paste.
I did it. Okay, just a minute. Yeah, I'll just
Mhm.
paste it in.
This is problem two. Problem one. Sorry. You are talking about the problem two, na?
Yes, sir. I'll also close mine and open it because from problem one, I can't go to problem two.
Yeah. Okay. No problem. I'm going to the problem two. Yeah. Only. Problem two.
Sir, 1 minute. I've just logged out. Just 1 minute.
Mhm. Okay, I'm not able to check. Okay, so you are not inside this problem two list.
Okay, 1 minute. So how do you go back to the
No,
main question?
you can just click on this back to dashboard, or let me open the student view. You can click on the top if you have opened any problem. So just like week 2, you can just click here and just go back from this.
Okay, week 2. Okay, week 2. Yes, sir. I pasted it in
Okay.
reply.
One second. Now this one. Okay,
Yes.
so
Yeah.
you are creating D equal to dictionary, new L equal to new list is you have created. For I in L1, if I not in D, Di equal to 1. Yeah, fine. And okay, you are just creating the count. Because we have the distinct elements, so no purpose of this. Okay, so elements are not repeating. Okay,
Okay.
so then after that, for I in L2, if
Yes.
I in D, new L dot
Yes.
append, return new
Yes.
L. So test
Yes.
case are not passes.
I'm doing it in the portal, and 2 out of 3 passed for the public.
Okay. So here what happened?
Let's say 2n, right?
Sorry?
Its complexity is 2n.
No, complexity is not, we not use this constant things. Okay, so here complexity is order of n. So just remove this two things if you are calculating.
So does it check the complexity? Because my test cases are passing. It is not showing me any
No,
error.
it is passing 3 test cases. Let me run again. The private test case. Yeah, it is working fine. On the portal, it is working.
But if you look at the, because it's something is showing 2 out of 3 for me. I'm not sure why. Public test case is showing 2 out of 3, and when I view details, it's saying timed out your execution code.
Okay, so yeah, because of that is happening because of this small test cases. Okay, so in some case, actually, what happened? Uh, that time is actually validating. Okay, for the small test case, if your that time is actually closer to the set time, so maybe sometimes it will move to the increasing side. Sometime maybe it will move to the lower side. So that behavior that behaves happens sometimes. Okay, so just run multiple times for this type of code.
Okay, I'll
Okay, but
refresh it. Okay.
yeah, but complexity is fine, order of n.
Okay, thank you, sir.
Okay, but because here what happening actually, we are just comparing the clock time. Okay, and suppose you are getting like microsecond time 1.133, and the set time is actually 1.1332, like this, very close actually. So according, based on the machine, sometimes it may be less, sometimes it may be higher. So because of that,
Okay, sir.
for a small input, this type of behavior may become. And by,
So if I remove the ends, will the time reduce?
no, yeah, it will affect little bit, but complex theoretical complexity will remain same.
Okay.
Okay, so why this is happening actually? Because if we compare the n square time, if we compare the n square time and n log n time, so the difference is very large actually, n log n. Okay, as we have mentioned for the large input. But if we, when we compare this n and n log n, so here the difference is not too much large. Okay, this is very much closer. Okay, so because of that, this behavior you are getting, because if you are rewriting the solution for n time, and suppose n log n is configured, so that means this is closer sometimes, and based on the machine, it may be sometimes your code will give some n plus 2, and not n plus 2, some like 3n or like this type of things, and maybe clock time will increase to this configured time n log n. Okay, but theoretically it is lesser. But some test case based on the machine, it may be increased like this 3n, which is greater than to the n log n. Okay, but for the large, very large input, definitely this n will be the smaller than this n log n. But for the large, very large input.
Thank you, sir.
Okay, so let's move to the third problem. So okay, So in third problems, here some
Sir,
scenario is given. Yes.
before going to third problem, I have doubt in problem 2.
Mm-hmm.
If I am using binary search and still I have to use for loop to iterate uh, first. Let's say I have sorted.
Okay, okay, that's fine. Then fine. Yeah. So what you are saying?
Means I mean to say I need two for loops, right?
Mm.
One for loop, so
Mm.
it will increase my complexity.
No, actually, if you have already sort the list, okay,
Hmm.
you already sort the list, one list now, correct?
Yes, yes,
So the complexity for that part is actually n log n.
yes.
If you are performing any operation below than this, so that
Hmm.
your loop is actually taking order of n time.
Hmm.
So overall complexity will remain n log n because the one operation is already performed with the higher complexity. So that will be considered as a overall complexity. So if you are performing any loop, that means that will not affect the complexity.
Okay,
Okay.
good.
Yeah. So complexity will remain in the n log n. Okay. So this is the third problem. So where some scenario is given to sort some, not sort. You have a deck of shuffled card. Yes, this is also sort things. Okay. Shuffled card ranging from 0 to this value, and there are two subordinate below you and two subordinate below them, and it goes on. Okay, so here some scenario is given how the work is actually divided. Okay, you have this range of cards, and below of you have two subordinate, and you will divide these problems into the half of the each. uh, okay, and then they will divide the problems half into their each their subordinate. So in this way this problem is divided. And what condition is given if a subordinate received only two cards. So in the when we are dividing these problems, at the last, if any subordinate received only two cards, so that subordinate actually will not divide further. Okay, not give the further to their subordinate, and he or she himself herself arrange in ascending order and give it back to the superior. And another condition is if a subordinate received only one card, then same things he will give back to the superior. So this is very similar problem which you have already learned in the week 2. So what we happening actually, we have n things. Okay, so we have n cards, and there is one subordinate here. Okay, and what he is doing, he is dividing this n problems into n by 2, n by 2 each. Okay, so this is the next level where two subordinates is required. So this is the second, this is the third. Okay, and again these are dividing into the further. So like n by 4 and n by 4, n by 4, n by 4. Okay, so this is like a fourth subordinate, fifth, sixth, seventh. Okay, but at any point in this process, if any subordinate receiving two cards, okay, so two inputs, so he will not further divide the problem. Okay, he will just sort these two cards and will return back. Okay, or if any subordinate receiving one card, he will return back. So this is the problem, and just think that which algorithms are best suitable for this, which you have already learned in the week 2.
Watson.
Yeah,
Sir,
correct. Yeah,
yeah, that's all.
merge sort, correct. So same process actually we follow in the merge sort process. Okay, we divide the problem into the half every time, but we divide till the point when we are getting one element at the last. Okay, so in the last, each actually list actually contains only one element. Okay, then we start the process of merging. Okay, but here what we are doing, we are just moving back from the this steps. If we are getting two, then we will sort these two and then we will revert back. We will not further divide. So here some modification is required if we are following the merge sort. We will not move till the one element.
Sir, how will you keep the count of the levels?
So that things not here. You no need to count the levels. Actually, you need the count of recursive calls. If you, what you can do, you can use the same merge sort algorithm here, but
So
just
global variable.
We just need to return when it's less to.
so here you need to count the recursive calls, how many calls are happening actually. Okay, and just also update this condition. If at any time your input list size is 2, do not further divide. Okay, just return back after sorting. Okay, and if you're getting only 1, then there is no problem, just return back as it is. So this updation is required, otherwise just use the counter for the recursive call. So this is your task in this. Otherwise, use the same algorithm merge sort in this. So sort the card, just follow the same purpose, but just modify the base condition of the merge sort recursive call. So let me open the merge sort algorithm and see what we can do. So here you can see we have this base condition. Okay, if n is less than equal to 1. Okay, so what we are doing, we are returning L as it is. So here you can add one more condition if n is equal to 2. In that case, sort that part. Okay, sort that list.
Sorry.
Sort that list. Oh, okay. So in this merge sort, actually, in this merge sort code, here, am I audible now?
Yeah, missed the part you said n is equal to and then.
So this part is already mentioned. If we are getting n is less than equal to 1, so we are returning list as it is. Okay, without doing anything. So what you can do, you can also add one more if condition where n is equal to 2 and return the sorted list. Okay, so if you are getting n equal to 2, that means 2 elements inside the list. Then sort that list. Then you can directly use this L dot sort. Okay, and return that list after. Okay, so that 2 conditions just used in this merge sort function. And to count the recursive calls, what you can do, you can take a global variable and inside this merge function, okay, inside this merge function, just increment that counter. So count equal to count plus 1, but use the global counter. So these 2 update is required for this.
Sir, which counter did you say?
Because here our target is actually to count this recursive call, because problem is how many subordinate is required, including you. So that means you need to count this, how many times this merge sort is actually called. Okay, so to count this merge sort, you have to take one global variable, global counter, and you have to increment that counter inside this recursive call, merge sort call.
Sir, but how to take global variable?
Yeah, you can just define that variable outside of this function.
Yeah, okay.
Okay. Or you can also do you can just, okay, so let me just check what is the required definition of the function. Problem number 3. Okay, so valid input. So here you need to write this function, and from the inside this function you can just call this merge sort function. So at the time of merge function creation, you can take one more variable in the recursive calls, so that you can also use as a global variable. Okay, so when you are calling this merge sort function from any subordinate function, okay, so what you can do, you can pass one more variable, that count variable. Okay, and just define that count variable in your subordinate function. or you can directly use, you can define outside of the main function and just use. Okay, so because of the so just also learn these algorithms. Okay, so here what you can do, you can copy the codes and this merge sort algorithms. But suppose if this problems comes in the OPP exams, so you should also know this merge sort implementation. Okay, so where you can write the complete code. Okay, so yeah, so let me just copy this code.
Sir, can you zoom a little bit because it's too small?
Yeah, this is portal page. So let me just, yeah, is it fine?
Yes, yes.
Okay, so I've just used this merge sort implementation. So what you can do, you can just define this required function subordinate, subordinate, and that one list L. Okay, inside from this function, you can call this merge sort. Now return merge sort. Okay, so return what is this? Okay. And counter is also required. No problem statement. What are the return value is required?
And the name of the function is subordinates.
Okay, yeah. And we need to return two value. No, your task is to find out how many people you are required to sort the card and print the sorted as also. Okay, so that we also require. So what we can do, so we can define one before this. We can just use one global counter c equal to 0 here, and from here we are calling this function merge sort L, and we will just return the value return merge sort comma c. Okay, so this c is now defined globally, and we are calling this merge sort function, and what output this merge sort function will return a sorted list, and same times we will also return the c. So what is the updated c we have? So from this final sorted list, inside the here we have to update this, so we will just increment this counter. So we have to use this global keyword, global c. Okay, and c equal to c plus 1. Now we have incremented this, and we have to take this condition. Okay, so if n is equal to 2, so then we will just write the sorted list. So if okay, okay, so L so if L of 1 is smaller than, okay, so smaller than L of 0, so this is the reverse condition. So if we are getting this condition, so we will return the reverse list. So return L of -1. Okay, so that means if our L1, second element is smaller than the first element, if this condition is true, then we will return the reverse list. Otherwise, we will return the same list. Okay. Okay, so this is the update. If we are getting two elements, then we are returning the sorted list with the two elements. Otherwise, if we are getting one elements, we are returning as it is. Otherwise, we are calling the same merge sort algorithms. So these changes are required. Let me test. Okay, yeah, these test cases are okay. Right, test case. Yeah, this is fine, working fine. Okay, so any query in this? What we are doing? We are just using one global C, and we call the main, this merge sort function from the main required function subordinate, and we are return C also. And inside this merge sort function, we use this global C and incremented this, and we update this condition according to the problem statement. The remaining code will of the merge sort will remain as it is.
So, sir, if we have to do merge sort, we'll have to write the previous all the code and then use it again. So the above code we'll still have to remember it.
Yeah, this code is required because we are also returning the sorted list in the output. Okay, so this merge sort is required completely because according to the problem statement, we need to return sorted output also. Okay, and with this sorted output, we need to require this how many number of recursive calls actually required. So that actually representing the number of subordinate according to the problem scenario. Yeah, so we need complete code.
So
Yes.
yeah, so can you that explain that return colon colon minus one? What does that
Okay,
do?
this is slicing just a reverse things. Okay, so this is a simply reverse operation. Suppose we have this list. Okay, if suppose we print this L colon colon minus one. So this is actually reverse the list. Okay, so let me clear this. Sorry. You can see this is completely reversing the things. Okay, so this is the slicing concept to reverse the list. Okay, so if we have two elements according to the concept of our code, so if we have this list, we are returning list as it is. Okay, because the elements are in sorted order. Suppose if we have this first element is greater than the second element, so in that case we are returning this reverse list after sorting this.
Yeah.
Okay. Okay, so this is problem third, and let's move to the problem fourth, last problem.
Sir, in my question 3, not working.
What happening? No?
Code not running.
Code not running. Okay, Sahil.
Yes.
So let me check. Yes, Sahil column 3. Okay. Okay, merge sort. You have this merge function is there. Subordinate function is there. So where is you define this count variable? If you initialize this anywhere.
No, sir, I didn't define.
So just define some outside of this any function, like in the last. Initialize with 0. Is it working or not?
Sir, not working.
Okay. So global count you have used count plus 1. Okay. And n equal to n, if n equal to 2, then L0 is greater than L1, then you return L, then you return L. Okay. If len of n, no, here are you taking any condition or not? This will be true if L is greater than 1, 2, 3, 4, anything.
Yes, sir. There I have to return equal to 1.
So you should clearly define this. Otherwise, this condition will be true for n equal to 3, 4, 5, 6, anything. Okay, so then you're calculating mid, left, left,
Yes, sir. Now for running.
working?
Yes, sir.
Okay, okay, yeah.
Sir, can you check my code? Like, I have implemented in
Mm-hmm.
like,
Dev,
yeah, yes, sir.
Dev equal 3, okay, this one. Okay, so here you have made the subordinate function like a merge sort, correct?
Yes, sir.
And where you define the okay, here you define, and you are using this return statement inside the else. Is it okay? Okay, let me check again. So global CO is this fine, incrementing is fine. If this list is okay, check this list of 0 is so, then return list. Okay, otherwise list selection. Yeah. Okay, if list length is list okay, else mid of line by 2. Left of list is made, right is distribute plus 1. Okay, sorted left, right of the subordinate right, return merge thing. Okay, and here merge inside this list. Oh, this is the counter. So why this is required here? List here return statements counter. Why this counter is required inside the merge?
No, sir. I just kept it to return. That's it. Nothing modified.
Here returning two value, and okay.
The merge function is the final returning function now, so that's why I introduced count over there. So to at finally to return the count in the output.
No, what you are returning two value from this function, merge function, merger, and but you are receiving the inputs only in one. You should write CO also here, no? If you are returning some things.
Yeah, yes, I guess I'm wrong myself.
So do not just pass this CO inside this merger function because there is no need.
Okay, so
Okay, because we are only counting this recursive call, subordinate recursive call. We are not counting this merge things. So you can just remove this from everywhere and just check.
Sir, but my function is wrong in the sorting, I guess. Like in the merge algorithm, I'm getting there on line 6, I guess.
Line number 6.
Yeah, sir.
No, this is condition. Let me run from my side 1 second.
Yeah, now it is showing fine, sir. I guess.
Some tuples value is coming. This 5, 10, 13 is fine. Okay, expected output and actual output. Your code is returning only list.
Yeah, count
Okay,
is.
okay.
So where should I introduce the count, sir? Like the take count.
So return merge this. So what you can do? CO. Then just take the CO here and let's see what will happen. Left.co. Line. Main line 3 is metal print subordinate this. Subordinate left. List one and left. Object of type int has no length. Okay, so list one and list two in the merger function. So list one and list two. Here what we are passing right. Right. Okay, so here we have also written this list dot co, and here we have also written co in the code. Not enough value to unpack. Expected to got one. Where from the left 07 and left. Any return statement? Still okay. This one. Yeah. CO. Now all return statements are returning two value now. Okay. Yeah, passed. Okay. Can you check this code on the portal?
Sir, I have a doubt in this 35 and 36. Why are we having two variables to have the
So
function?
because we are calling this function from here. Okay, and here actually what we are returning this two value from the merge function. Okay, and two value we are returning, so that means this merge function, when you call this function will return two value, and this function, that two value should be passed here for the variable, because
Oh, okay,
okay,
sir. To hold the
for the two
returning
value.
value. Okay,
Yeah,
okay.
so sometimes because we are getting two value from maybe this return statement, maybe this also, maybe this also, and maybe this also. So all place we have to return two value to unpack properly.
Yeah, okay, sir. Thank you.
Okay, yeah.
Yeah, sir.
Okay, so let's move to the last column. Let's see what is this. This, yeah. Okay, let me write this column statement. Okay, so this is problem 4. Given a list L of random numbers and another number pair sum. Find whether there exist two numbers in the list such that their sum is equal to pair sum. Write a Python function find pair L and pair sum that return true if there exists a pair of the integer in L whose sum is equal to x. False otherwise. Try to write a solution of n log n or better. Okay, so hint is also given. Try to sort the list first. So this is one way, and another way is also possible for order of n time. So can anyone just tell me any logic for this?
Sir, I have tried it by using dictionaries.
Yeah, that is also one approach.
Yeah,
Right.
I have made a dictionary and collected all the values of L and initialized to one, and
Mhm.
then I iterated the list and checked for each element in the list if the difference between the pair sum and the element is found in the dictionary.
Yes,
If it
correct.
is found, I will return true or else false.
Yeah, that is order of n operation. So that is best operation. Yeah, correct.
Sir, can you
So
check my? I've written it in Replit.
for problem 4,
Yeah,
okay, Tarang. Dev or Tarang? Who said?
sir, Tarang.
Tarang, sir.
Tarang, okay. Tarang.
It is 23F20046661.
Okay, where it is? What is last 4?
4661.
It is not visible here. Okay. Undefined name. Some error is there. Your code is working or not?
Sir, sorry. Instead of L1, it will be L.
Okay. It is working?
Sir, I checked it. It one of the outputs it was working, but
No, it is failed for all. Okay.
sir, can you just check the logic because I think it's right.
So first you are sorting the list. After that, for I in L equal to 0, H of L. So you are using binary search here?
Yes.
Okay. middle element, then if L equal to h, I plus lm is equal to pair sum. So I is representing the element, okay, first element you're just looking for, and then lm.
Sir, it should be big L. I've written small.
Here also?
No,
This
not there.
is okay. L and all are okay. Yes. Then it is going, I think, in infinite things maybe.
Sir,
No,
could you
what is your logic? Can you just explain what you tried actually?
Yes, sir. So we'll take an element,
Hmm.
then we'll go to then we'll use the binary search. So it will take the middle element, then it will check if the middle element and the first element are summing up, means they are equal to the pair sum. Then we'll return true, or else pair sum, or else the number minus sum. If it is in L, we will continue, and if it is greater than L, then the normal binary search technique.
It should be in line number 10, there should be return, right?
That is also one thing. And apart from that, you are using binary search here, okay? But inside this, you are using this one operation, this in
Yes.
L, but it is a linear operation. Okay, so there is no meaning of the binary search things if you are using this linear operation for this.
Sir, could you check my code?
Okay.
Okay, so just, yeah, you are going to the in the correct way, but do not use here to the binary search. I think binary search will not work. Okay, because you have already done one L sort that is taking n log n time. So if you are using binary search, so that will not improve too much. So you can try the linear operation after this.
Sir, could you check my code?
Bablu,
Yes, sir.
this problem 4.
Yes, sir. One test case is failing.
Okay. Oh, very short code. For x in L, if pair, okay, so this is for loop for L, if pair in L, return true. But this is n square code.
Sir, you can check someone else's program. I'll check on it.
So this is Bablu, this is n square solution.
Okay.
Okay, because you are just going through each element and you are checking the same things. If you are using this in operation with the L, this is also a order of n operation inside this. So n of n by n is equal to n square.
Portal, sir, it passes all test case.
It will pass because here we are not testing the complexity for this, I think. Some code actually we are not testing. It will pass. Yeah. Your code is working fine, but the complexity is not as the required. What you can do one things. You can make the dictionary for this list. Okay. So what you can do, you can make the dictionary for this list in the one iteration that will take order of n time. After that, you can do the same things. Okay. Then at this line, just use the dictionary at this place of this L. Then it will become a constant operation. Okay, so what you can do, you can just create it like for for I or I in L, just create a dictionary. So, so what is this? Suppose you have to create the dictionary first. T of I equal to 1. Okay, and here use D. Okay, so now this is actually a order of n operation. After that, this is a iteration of the each element, and then when you're checking this pair m minus x is in D, this is now constant operation in the dictionary. So this will remain the linear operation, order
Sir,
of
I
n.
have done the same thing, but the fourth test case is not passing, sir.
Let me check this. No, it is working fine. Can you check what change you have done in your code, logic wise? Or so here I am creating one dictionary, then just is creating a key for the dictionary for each element, and after that traversing each element from the list and just checking if pair sum minus x in D or not.
When the pair sum is 1, and that is the only one is the only element in the dictionary, then it is finding another one. I mean, I have done the same thing. Then this is giving me true, whereas it should give false.
Now, what input you are considering?
So I have done the same thing. What is on this?
Okay, let me open your code.
My, what should I say? Last 4 digits?
Yeah, so what's your replit ID?
So it's my roll number. So should I
Tell
say
me your
the
roll
last 4
number.
digits?
Yeah, tell me your roll number, last digit, or
It's last 4 digits are 3016.
3016. Okay, yeah, this one. But this is problem 3. 1 second. You are solving problem number 4 now?
Yes, sir.
Yes. Okay, dictionary, then for in L, D, I of equal to 1, for I in, for J in L. If PS else first. So what is this else actually? This is not for this if.
No,
This
sir.
else
This is
is
for for. I mean, if for continues to iterate successfully, then this else will execute.
but I think it is not required. Let's just change this. Okay. Yeah, it is working.
So the fourth.
Okay, fourth is failed. Okay, okay, yeah.
Yes.
Okay, L pair sum D in L D equal to 1. If J in L D return true, else is return false. Let's check this code on the portal. Okay, portal it is working, but here it is failed. So why? What is the input?
It should fail, sir. I want to ask how to overcome this. I mean,
So
I
in
am typing the difference
I
in the dictionary, and it finds the value, the difference value in the dictionary. That is 1. That's what it's
sir,
doing. That
sir,
yeah, 1 second. So here this is the input list, and 2 is the pair sum, and okay, so
when
okay,
it comes
okay.
to 1, value 1, I'm
Ha.
calculating the difference and finding, and the difference is 1. So it is finding there. That is why it is giving me true, whereas it should give false.
Yes, yes. So this is the corner things.
sir,
Yeah.
I just added another condition for school. Like the school is very much similar to mine.
Mm-hmm.
Like I have made like if difference is not equal to like L of I, like here is J, I guess.
Okay,
The
then I
difference
should
is not equal to the element. So
iterate by value. I mean the index value, not the list. Yeah, yeah. Okay,
So
sir. Yeah.
any condition is given that all elements are distinct.
So I have to. I got it, sir. I have to iterate the for loop by the index number, not by the value. Then it will not happen.
Yeah, that type of constraint we can apply. But is there any another way to solve this? So for n log n solution, we have another way. So as according to the condition we have given this. So what we can do, we can apply the things like after sorting the elements. Okay, so we can decide. Let me just explain this. Suppose we have any list. Okay, so like any input list. Let me just take one input. So like this. 21. So what we can do, first thing we can sort this list. Okay, so 10, 4, 11, 5, 1, 8, 7. This is the list given L equal to, okay, and pair sum equal to given as a 21. So what we can do, we can sort this list first. So L will become 1, 4, 5, 7, 8, 10, and 11. Okay. And after that, what we can do, we can set our count one pointer. So left, like left to this element and right to this element. Okay. And we can just add these elements, left plus right. Okay. And based on that, we can decide this side we need to move. So here, if suppose, if we are getting this L plus sum, this left plus right, if this sum is actually less than to the pair sum. Okay, so here we are what we are getting this 1 plus 11. If this value is we are getting less than the pair sum, so we can increment our left value to the right. Okay, so if we are getting the sum of L plus R, which is smaller than the pair value, so we will increment our left plus equal to 1. So then we will move to this side. Okay, and then we will check again same thing. So 4 plus 11 is still lesser than the 21. So then again we will do the same things. We will increment the left things. In some case, if we are getting the higher value, okay, then that case we will reduce this right to the left side. So in this case, in this way, we can get the thing. So like 5 plus 11, we are getting 16, still less than. Then we will move to this. Okay, then 7 plus 11 is 18, still less than. Then we will just check for this. Okay, so 8 plus 11, 19, and not getting then this 10 plus 11. Yeah, here we are getting the solution. So if anytime we are getting this sum is equal to pair sum, then we can return the true. Okay, otherwise if after completion of this process, so this left and right, so we will run this while loop when we are getting left is less than equal to right. This will be the condition for while loop, and in every time we will check if our this sum is equal to pair sum, then we will return the true answer for this. Otherwise, we will just increase shift this left or right according to the condition. If we are getting some less than, then we will shift our left to the right. If we are getting some more than, then we will shift our right to the left one position. So this is only a one iterative way. So we are just iterating this list linearly, and before that we have done one sorting thing, so that n log n actually that is taking, and this operation is only performing in order of n time. So overall complexity will remain n log n. So in this way you can also check the you're getting this any sum pair you have or not in the list. Okay, you can try this approach also, but the complexity for this is n log n. Otherwise, the complexity with the help of dictionary things that will order of n, that is better. Okay, so you can try this approach also.
Yes, sir. My code is doing like this only.
Okay, if your code is working fine and complexity is n log n, then this is fine.
Yes.
Okay, so you can try this, and also after solving this problem on the Rapid, also save the code on the portal. Okay, so for the backup purpose.
So,
Yes.
sir, can you please explain that second problem about that sets?
Second problem today.
Yeah, it's that one about the sets.
Let me 1 sec. Intersection of the list.
Yeah, using sets, someone sets.
So I've explained using the dictionary, but you can also use the sets, because sets also contains that same concept hashing. Okay, so you are asking especially for with the help of sets, or
Yeah, I just been using sets because I done by your way using dictionary, but how sets can be done? How using
okay,
sets?
okay. So with the help of sets, yeah. So two lists you have. Okay, so what you can do, you can write. So this is okay. So find common A. So this thing. So you have A and B list. What you can do, you can create a set for one list. Okay, so S equal to set and pass the A. Okay. So for the second list, just check the for I in B and create one another list to return the output. What we are expecting answer this are common elements. Okay. So let res equal to empty list.
Sir, can't we assign both the list a set and then we can do intersection?
No, why that is another set why that is required. Yeah, you are saying that just asking the set operation to find the interest that things. Yes, set also supports some these type of operation to find common elements and find intersection, union. That you can also use that, but here we are trying to solve using different approach with the complexity. But because we don't know how much time that set operation actually will take built-in function. So here actually one set is required because another list we will simply traverse that will take order of n time. So that is fine. So by default this is also taking when we are creating the set for any list, that is also taking order of n time. Okay, so internally. So here I in B, we are reading the elements from the B list. If here we'll take if I in S. Okay, so set. If this is true, then we will append the result into the R. So res dot append I. Okay, and in last, after completion of this, we will return result. this common list. Okay, so let's check this. Let me check this on the space. Okay, it's to failed. Exit time. Okay, so this that thing, yeah, is some. Let me run again. Passed. So because of that, this is very close time for the small input. Because of that, some time is random behavior is coming. Otherwise, the code is fine. Okay.
So
So
here the what will the in's time complexity will be? So like in dictionary it will be constant, but in set
same things here. The complexity is also order of n. Okay.
So quantity n square like iterating through the set.
So what happening actually? We are creating set for the first list. Okay, so set is actually reading the elements from the list and inserting into the set. So that is it a single linear operation. So this operation when we are creating the set is actually a linear operation order of n. After this, what we are doing, we are simply reading the element from the v one by one, and we are checking this element is exist in the set or not. So this operation is actually similar to the dictionary operation. So here when we are checking this I is exist in the S or not, so this is actually checked in the constant time, order of one time in the set. Same similar to the dictionary. Okay, so same if we change this, like what we can do, we can just write like this D, and we can create a dictionary for this DIC3. I'm not sure. I have not used this shortcut things. So let's see what is behaving. Oh, so here we are getting error. Okay, so we cannot convert the sequence like this. Okay, so we cannot convert sequence because the list is contain the single value, but we need the pair of the value. Okay, so key and pair. So we cannot directly convert into the dictionary in this way, but we can convert into the set. So if you want to convert into the dictionary, you have to traverse one by the loop for I in J, for I in A, and then create the key. But here, if we are using this, I just said, then it will work. So you know then how we can create a dictionary for the list? We have already created for some problems. What you can do like this. So like DIC equal to dictionary, and after that for I in A, just create the key for this. Okay, DIC of I equal to anything. Okay, so you get just like one. So now this DIC dictionary is created. Now you can make this comment and DIC. Okay, so now it will work. So now it is working similar to the previous code. Okay, so now we are creating the dictionary where we are just creating the each element of the A as a key of the dictionary. Okay, then after that we are searching this I in tick or not. So this is also a constant operation. This operation is a constant operation in dictionary. Okay.
Yeah. Okay.
Yeah. Okay, so I hope all problems are discussed. Now you can try by your own if you have not done. Okay, on the portal itself with the new user interface. Okay, any query, anyone? Or we can close the session already 3 hours. Done. Okay, if there is no query. Yeah.
Sir. Thank you.
Sir. Okay. Yeah, thanks everyone. Good night.
Thank you, sir. Good night.
Good night, sir. Thank you.
Good night.